This is the solutions to assignment 6B. Question 1 gives us this curve and asks us to sketch it out for them. So there's a couple of ways of doing this. The first one is on your GC. You can go to the mode, set it to parametric, key both of these in. Please just remember, however, to make sure that you also change your view window so that the T minimum is set to 3. Otherwise, you will get the wrong shape of curve, or the curve may or may not make sense. However, if you don't feel like doing this, there is an alternative. This doesn't always work, but it does work in this case. We can make t the subject of this equation, so x equals to ln t. That means that t is equal to e to the power of x. That means that y is equal to the square root of e to the x squared minus 9, or y is equal to e to the 2x minus 9. And we are perfectly able to sketch this graph. So I'm going to show it to you now on GeoGebra. This is what it looks like. Now, when doing this, please pay very careful attention to the curvature. If you have not set your view window right, this could look several ways. It may look like it's bowed outwards, so that it's increasing at a decreasing rate, or it may look like it's bowed this way, so that it looks like it's increasing at an increasing rate. The truth is actually somewhere in between, and you can see it more as I change the scale on the y-axis. Very close, it's actually vertical. So right where it's touching, it's basically going straight up, then it decreases, but it comes back and curves up again. So try and get this type of curvature showing clearly on your graph. And again, you can do it using this Cartesian way if you're not comfortable with the parametric coordinates. So let's look at part 2. The finite region S is bounded by the curve and the line x equals to ln 6. So again, if we come back here and we look at the line x equals to ln 6, cancel. X equals to ln 6. You can see that the region that we're looking at is this region in here. Now, in particular, that means that I'm integrating this curve between x equals to this point here, which is ln 3, and this point here, which is ln 6. So I have to show that the first part is to show that the area can be expressed like that. So let's do that. In general, the area of S is going to be the integral from ln 3 to ln 6 of the absolute value of y dx. Now, we don't need the absolute value here because y is strictly positive. So this is just the integral from ln 3 to ln 6 of y dx. That's the integral from ln 3 to ln 6 of the square root of t squared minus 9. This doesn't help us if we're dx, so we need to change from dx to dt. We know that x is equal to ln t, so dx dt is just going to be 1 over t, doing integration by substitution. That also means that instead of going from x equals to ln 3 to x equals to ln 6, we're now going from t equals to 3 to t equals to 6. Square root t squared minus 9 dx dt dt. And when we simplify that, this is the integral from 3 to 6 of the square root of t squared minus 9 over t dt. So that's what we tried to show, and that also means that p is 3 and q is 6. So now we need to use another substitution, t equals to 3 secant theta, to solve this. So let t equal to 3 secant theta, then dt d theta is going to be 3 secant theta tangent theta. So here we go again. So integrating. Now, how do we get secant theta to equal to 3? That happens when theta equals to 0. How do we get it to equal to 6? That happens when secant theta is equal to 2, which means that cosine is a half. that happens at pi upon 3. So we can now substitute in our terms. This is the square root of 3 secant theta whole thing squared minus 9 divided by 3 secant theta times dt d theta d theta. So what's that going to be? That's the integral from 0 to pi upon 3 of 3 square root secant squared theta minus 1 over 3 secant theta. Dt d theta is 3 secant theta tangent theta. So we've got 1 3 spare, but this 3 secant theta and this 3 secant theta can cancel out. Secant squared minus 1 is just tangent squared. Square root of tangent squared is just going to be tangent. So this is 0 pi upon 3 tangent times tangent d theta. So this is tangent squared theta d theta. Again, simplifying further, we know that that's going to be 3 from 0 to pi upon 3 of secant squared theta minus 1 d theta. And so, what do we get? 3 secant squared integrates to be tangent, 1 integrates to be theta between 0 and pi divided by 3. And that gives us the final answer of 3. Substituting 0, both these terms will be 0, so we just get tangent of pi upon 3 is root 3 minus pi upon 3. Or expressed alternatively, 3 root 3 minus pi. Okay, let's move on and let's have a look at question 2. Question 2, first part, tells us this region, asks us to verify that the x coordinate of point P is pi upon 4. We don't need to show this, we just need to verify. So when x is pi upon 4, sine pi upon 4 is equal to 1 over root 2, and 1 over root 2 tangent pi upon 4 is 1 over root 2. Therefore, x coordinate of P is pi upon 2. So we've verified. And we don't need to show, we don't need to calculate, we just need to substitute it in and check. And that's what it means to verify something. So if we come down, find the exact area of A, giving your answer in the form A plus B ln 2. Okay, so the area of A is going to be the integral from 0 to pi upon 4 of the top line, which was sine x dx, minus the bottom line, which is 0 to pi upon 4 of 1 over root 2 tangent x dx. So integrating sine, we get minus cosine x between 0 pi upon 4, minus integrating 1 over root 2 tangent x, we get ln mod secant x between 0 and pi upon 4. Just briefly, a few of you guys may get negative ln cosine x instead. This is exactly the same thing, because remember, this is actually just ln cosine x to the power of minus 1, which is ln 1 over cosine x, which is ln secant x. So we are talking about the same thing, it's just there'll be a change of sign. If you've got cosine, this will be positive. If you haven't got that, then don't worry. Okay, so now we can substitute our values in. Cosine pi upon 4 is 1 over root 2, so we get minus 1 over root 2 minus negative 1 minus 1 over root 2. If we substitute in 0, we get ln of 1, which is nothing, so we just substitute in pi upon 4. This is ln 1 over root 2. So that is 1 minus 1 over root 2 minus 1 over root 2 ln, and remember we have to express it as ln 2 to something, so this is ln 2 to the negative a half. So we've got 1 plus 1 over root 2 plus, bring that half down, 1 over 2 root 2 ln 2. So answering the question, therefore A is 1 plus 1 over root 2 and B is equal to 1 over 2 root 2. Part C, sorry. Yeah, part 3, sorry. Don't know why that's changed to 3. Find the exact volume when the region A is rotated 360 degrees about the x-axis. So the volume when rotating about the x-axis is pi. Take the two bounds, 0 to pi upon 4. Take the larger one first, so in that case it's sine. Square it, and then subtract away the other one. So we can't put them both underneath the same squared sign. Has to be separate squared signs, so please be careful to do that. Okay, but this is not too difficult because we can transform sine squared, although we usually can't do this. We've done it a few times now. We use the double angle formula to change it to something we can fairly comfortably integrate. 0 pi upon 4 of tangent squared. Tangent squared don't like, so we change it to secant squared minus 1. So this is pi times x minus a half sine 2x between 0 and pi upon 4 minus pi upon 2 tangent x minus x between 0 and pi upon 4. So that works out to be pi upon 2 pi upon 4 minus 0, you get pi upon 4, pi upon 2, which is 1, so minus a half. Substitute in 0, you get nothing. So minus pi upon 2. So substituting in, you'll get, when it's 0, there's nothing, so just have to substitute in the top one. Tangent pi upon 4 is 1 minus pi upon 4. And simplifying, that's going to be pi squared over 4 minus 3 pi over 4. Okay, very last question. We need to find it about the y-axis, but pay attention that they only want us to give it to 4 decimal places, and we need to, we've changed the axis. So 4dp means that we can use our GCs to help us out, so it's just a matter of rewriting the equations. So if you noticed back in this original one, when we looked at the graph, we found that the coordinate here, the x coordinate is definitely pi upon 4. The y coordinate was 1 over root 2. So we're going to integrate from 0 to 1 over root 2. This time we have y equals to tangent x. That makes x is equal to tangent inverse of y root 2. And then this is actually the one underneath this time, so x is equal to sine inverse of y. So we're going to use these two functions. Remember, integrating about the y-axis, we integrate x squared dy. But we can use our GC to do the heavy lifting for us. So this is just the integral of pi times the integral from 0 to 1 over root 2 of tangent inverse root 2 y squared dy minus the integral from 0 to 1 over root 2 of pi times, of sine inverse of y squared dy, and from our GC that is 0.128024 dp. And we're done.